Hello, everyone. I think we're live now. I sent the link out on Slack, so if you're watching live, I'll also pull up here. I think there's a chat window. If you see the chat window on your application, feel free to enter in any comments or questions you might have, and I'll try to address them if I see it during the seminar today, or if not, I'll check it at the end. Also remind you that if you're watching live, we'll have a Ask Me Anything session immediately following the webinar. That'll be on Slack, so stay tuned there and ask any questions about something in this particular seminar, or any questions you have on any topic in this nano degree program. So with that, let's go ahead and get started. I have some slides here, and we'll go through those. The topic today is, let me pull this up here just a second. Okay, I think you should see the title slides here. The topic today, as you can see on the slide, is the Markov decision process, and be covering really just the key points of that process. And with that, let's go ahead and get started. The objectives today is to review the basics of reinforcement learning. Everything in reinforcement learning is based on the Markov decision process. It's really the foundation for everything we do. So we'll review the basics of the MDP. This includes an agent and an environment principally, and then the states, actions, and rewards that make up the interactions between the agent and the environment. And then we'll discuss state value functions and action value functions. They're similar in a lot of respects, but they have some slight differences that we'll talk about. And then we'll discuss the concept of a policy for an MDP and what is meant by the optimal policy, of which there may be more than one, but typically a single optimal policy. Well, I shouldn't say typically. Often they do actually. There is often more than one optimal policy. But we'll describe what is meant by that. So our RL basics, reinforcement learning basics, in essence, this is really MDP basics: the agent, the environment, action, states, and rewards. Now, if you tune into the last seminar, the last webinar for this nano degree that I gave a couple weeks ago, I introduced this figure from our textbook, Sutton and Bartow. It's probably the most important figure in the book. I think I mentioned that at the time, and just to reinforce that today, the MDP really consists of these two main components: the agent and the environment. The agent takes an action, denoted here on the right-hand side of this chart, A sub t, and the environment responds with a next state and a reward for taking that action in the previous state. That next state and next reward signals come back to the agent, and the agent looks at that information and decides what action to take next in its quest for solving that environment. So the key terms, again, this is a summary from the last webinar, but we'll go through these fairly quickly before we get into the new information today. The agent is this hypothetical entity that basically can perform actions and get some reward for performing those actions. And those actions are all the different possible things that the agent could do. It's its only way of interacting with the environment. And that environment is the scenario that the agent faces. And his quest is to solve that environment to achieve the maximum reward that he can. In the process of achieving those rewards, and getting the best return possible over time, the agent's sort of quest is to solve that environment and to efficiently achieve the goals that the designer of this setup placed in front of the agent. The state information is the current situation that's returned by the environment. The state's the only thing the agent has to look at to understand the environment, so it has to encapsulate everything known about not only the current situation, which is really what it represents, but that state information has to be complete enough that it really represents everything that's happened in the past in some way. The reward is the immediate, it's a very short-term return. It's the return for that one action that was taken in the environment in the state that the agent was last in. The policy is a strategy that the agent employs to determine what actions it's going to take based on what state it's in. And a lot of what we talk about in reinforcement learning is coming up with good policies. And there's lots of different types of policies. We'll talk later on about, well, we actually discussed, I think, last time about the multi-armed bandits greedy policy, which is basically always take the action that you think, based on your past experience, will give you the best return. There's an epsilon greedy policy where you don't always take the best policy that you think you know about, because if you do that, you might lock yourself into a short-sighted situation where you may think you're getting the best return, but there may be another state out there or another action you could take that, although you may currently think is not that good, in reality may be very good. And so an epsilon greedy policy would let you trade off some of exploitation with some exploration, and let you actually explore the environment some in some situations, and some with some probability, but then also take the optimal policy in other situations, other probability of taking that chance of doing a greedy action. So again, we'll talk more about that, not really today so much, but in future webinars, we'll talk a lot about the different policies that you might be faced with. Today, the ultimate thing for policy is to understand what a optimal policy is and what's meant by the optimal policy. So we'll get into that towards the end of today's lesson. There's two types of value functions that we'll discuss today and are important throughout all of reinforcement learning. First one is the state value, and that's the expected long-term return that could be discounted, and we'll discuss what we mean by discounts here in a minute. But it's the return for being in a particular state while following a particular policy. So B sub pi of S is the return you expect to receive for being in state S following policy pi. Now, related to that, sometimes you might want to take into account not just the state that you're in, but of the actions that are available to you in that state, what value is achievable by taking any of those specified actions. And if you look at it from that perspective, then you're talking about the Q value. So the Q value takes into account not just the state, but also the action that you would take in that state. So again, the summary at the bottom there, Q sub pi of state action pair refers to the long-term return that you would expect to achieve by being in state S, taking action A, and then thereafter following the specified policy pi. So some key points. Excuse me, the agent and the environment interact always at discrete time steps 0, 1, 2, 3. So every one of these actions take place in a discrete time. And at each one of these time steps, the environment is going to provide to the agent information about the state that it finds itself in. And this agent will then review this information, the state information, also have visibility into actions that it may have previously taken, or its understanding of what return it might expect to see by taking various actions, or what return it might expect to see by being in the state, and then choose an action to take in that state. One time step later, the environment will then provide back to the agent a reward and a next state that it will go to. So in summary, at the bottom there, you see a pretty important equation for defining what P of a next state, which is termed S prime here, and a reward given a current state and an action. It's equal to the probability that you'd find yourself in that next state and get that reward, given that you're in the current state and that you take that specified action in the current state. So looking at that equation, you can see that the probability of each possible value for S sub t and RT depend only on the immediately preceding state, S sub t minus 1 action, 8 sub t minus 1. So that is a key property. It only depends on the current state in action, nothing else about things that have happened. So that implies that the current state has to include information about all aspects of the past interactions that the agents had with the environment that might make a difference for evaluating what might happen in the future. And if that is true, if that's the case, then the state is said to have a special property called the Markov property. So some insight on what we've seen so far here. Actions are any decisions that we might want to learn to make. And states could be anything that we know that might be useful in taking those actions. And in fact, the state's information that you have is the only thing that you know about the environment. So the state information has to be inclusive of all the things the environment might want to feed back to the agent. So a general rule here, anything that can't be arbitrarily changed by the agents considered to be part of the environment. The only thing that the agent can do is specify an action, and the rest is left up to the environment to evaluate that action, determine what the consequence of that action is, to determine what the next state is, to determine what the reward is. All those things are part of the environment. Another insight is that you're not limited to having a single agent. You can actually have multiple agents interact to solve a bigger problem. I think we'll talk about next week an interesting paper that was written that talks about a tree-based approach to having agents interact with one another. And we'll talk about a particular example from that paper. The taxi problem is sort of a famous problem in the reinforcement learning world. Back to the multiple agents, though, as an example, you might have like an agent that does some high-level planning and makes decisions at a high level, and that high-level decision, the state that you find yourself in from that high-level agent, that could become actually part of the state information that you feed to lower-level agents that they might use in implementing the high-level decisions using some lower-level actions that achieve the overall goal of solving the environment. One thing I'd like to point out is that although there's a lot of science in the theories, there's a lot of science in the different algorithms that we'll talk about throughout this reinforcement learning nano degree, a lot of what we do in this domain is art. And that comes from defining the states and actions that are available. When you put together an environment that you want to solve, as an engineer, you really just have the problem that you're faced, and what you're given are some algorithms to choose from, the science part of it, but then the art comes into play in designing that environment, designing the rewards that you're going to provide, designing what the different things are that the environment can provide to the agent in terms of state information, and really determining all those things, determining the states that you can have, the actions that you can take, the rewards that you provide. They are all the things that you have to provide to the agent, and as an engineer, those are the things that you have to take great care in crafting and really use a lot of ingenuity in to designing in order for the agent to have any chance of solving the environment. And that part of this nano degree program, we don't really spend a lot of time on. Most of those situations are given to you as part of the problem set. Most of those situations are things that either the textbook has provided as an example or have been already canned problems that have been set up for you to solve. And throughout this nano degree, we really spend a lot of time doing the science part of it, but I just wanted you to be aware that the art is really just as important. And if you happen to get a job in this domain, you're going to spend a lot of your time using that science, but spending a lot of your time actually developing the art, developing those different states and actions and determining reward signals. And it's a lot of the art that takes a great deal of time. So just a point to emphasize here, a difference between a goal and a reward. A goal is really a longer term thing that you're trying to accomplish, and reward is really a very short-term signal that you're given to the agent from the environment. So at each time step, as the agent interacts with the environment, that reward signal, R sub t, the reward at time t, it's just a simple number. It's a single number. All it is a single real number typically. It could be an integer in some problems, but in most general problems, it's a real valued number that you are given from the environment. It's not a very complicated thing. It's a very simple signal, but that signal is the only thing that you have to work with to solve the environment. So Your goal as an agent is to maximize the long-term cumulative reward, not just that short-term reward, which is what you see, but the cumulative long-term reward. So as an example, if you were designing a robot to learn to escape from a maze, you might, as the engineer designing this problem, define a reward of -1 for every time step that the agent finds itself in that is not the terminal escape state for the maze. Defining the reward in that way, the rewards keep accumulating over time and get more and more negative. So that would encourage the agent to maximize the return by finding the fastest route out of the maze. And if it found its way out of the maze in 10 steps, it would find a score of -10. Whereas if it took 20 steps, it would find a score of -20, and would find that the better return for that overall process, or that overall episode, was the one that only took 10 steps. So that's just a common type of reward of including something that has a negative reward for time. In this particular one, that was the only reward, but sometimes you might find that included in a piece of the reward that you summed up to provide to the agent as that one reward signal number. So the overall design strategy as an engineer designing a problem like this is to craft rewards in a way that if the agent maximizes that reward, then as kind of a side effect, the agent achieves the goal that you set before it. So here's a warning. It's sometimes it's easy to fall into a trap where you try to define reward signals that sort of try to guide the agent into influencing how it achieves the goal, and you don't want to do that. You don't want to constrain or try to push the agent in a particular direction that encompasses how to achieve the goal, but rather craft the rewards that influence them to achieve the end goal. As an example, I think this is an example from the Sutton and Bartow book. If you were designing a chess-playing agent, you should only reward the agent for winning the game, not for achieving a lot of sub-goals like calculating piece values or king safety or mobility, the kinds of things that in the past AI engineers have used to try to develop game-playing heuristics. So one thing that the AlphaGo team did when they crafted the AlphaGo chess playing program was they didn't include any of those values. They only gave it the reward for winning the game. And as a consequence, the chess playing program that the reinforcement learning world was introduced to, AlphaGo, actually plays chess in a different way than humans play chess, and has provided a lot of insights into better ways that humans can play the game. And if the researchers had constrained the agents to include these traditional things like piece value and king safety and mobility, then that reinforcement learning program might have played more like a human, but it would not have been as powerful as it turned out to be. And in fact, that AlphaGo program that was dealt with reinforcement learning is today the most powerful chess playing program in the world. So in summary, when you're creating a reward signal to provide to your agent, you really need to concentrate on communicating what you want the agent to achieve, but not try to incorporate into that how you want the agent to go about achieving it. It's an important distinction. So a comment here about episodes, what's meant by an episode. Episodes end in a terminal state. So the example given earlier with the robot that's trying to find its way out of the maze, once it reaches the exit cell of the maze, then that's the terminal state and the episode ends. Whenever you have episodic tasks like this, then whenever you reach the terminal state, the system resets back to a standard starting state and begins again. The starting state could be always the same, or it could be a distribution of starting states that you would randomly choose from using some heuristic, some statistic. But the key thing is that whenever you return to that starting state, you do not take into account any of the information about how the agent did in the previous episode. So each episode starts anew with no history impacting the starting state based on how it did in some previous episode. So every episode is independent and stands alone. It's an important aspect of reinforcement learning. So now we're going to get into a little bit of math here. This is might look a little intimidating, but it's not really. We're going to talk about continuous tasks and discounted returns. So if the previous slides talked about episodic tasks, where the episode has a natural ending point. If the episode doesn't have that natural ending point and would go on forever, we would face a problem where the rewards would continue to accumulate and could grow to infinity. It could be positive infinity or negative infinity, but they would continue to grow. So that cumulative reward needs to be constrained in some way in order for the agent to learn. So to introduce into continuous tasks a mechanism that would let us learn in that situation, we introduce a concept called discounting. And to discount future returns, we have a discount rate gamma, where the total return, which you see in this equation here, G sub t, is defined to be the return that we get in the next state plus all future returns discounted by gamma, where each future return has gamma multiplied by itself or raised to a exponent here. That is the time step that you're referring to each time. So future returns, we get smaller and smaller and smaller contributions to the total return if gamma is less than 1, and gamma is always less than 1. So gamma, it determines the present value of the future reward. That's called the return, G sub t. So we have two types of agents. This kind of gives us a myopic or short-sighted agent. Has gamma equal to 0. So if you look at that equation and set gamma to 0, all the future rewards are not considered in the return, only the nearest return for the most recent action. So that's considered a myopic agent. So you're only looking at the current return, very short-sighted view of the world. A far-sighted agent, if you set gamma to something closer to 1, and the closer you get to 1, the more the agent starts to look at future rewards and consider future rewards in its analysis, then that's called a far-sighted agent, because it takes those long-term rewards into account when it's making its short-term return decisions. So here's an interesting relationship. That first line is just the definition of the return. It's the current return plus the discounted future returns. If we pull gamma out of that long list of future returns, you see that we get a relationship shown in the second line. And if you look at that, what's in parentheses there, you see that return is actually the definition of the return G sub t plus 1. It's the return of all the future discounted returns for the next state that you find yourself in. So in summary, on the last line, we can express that as the return in the current state is equal to the return, the reward, the reward we get for taking action in that state, plus a single discount of all of the future return that you get based on that transition. And so it's a very interesting relationship. And it's an important equality that is used for making a lot of proofs in the theory and algorithms of reinforcement learning. So now a new topic here. Let's talk a little bit about policies and value functions. A value function is a function of the state, or if it's a Q value function, it's a function of the state and action that's taken in that state that estimate how good it is for the agent to be in that particular state, or for the Q value version of this to perform a given action in that state. And value functions are always defined in terms of particular ways of acting, and those particular ways of acting are called policies. So you'll see all throughout reinforcement learning the concept of a policy, and if you're following a particular policy, you do one thing. If you follow a different policy, you take a different set of actions. So here's that distinction I mentioned, state values versus action value functions. A state value function for a state S acting under a policy pi, that's denoted to be B sub pi of S. It's the expected return that you expect to see for starting in that state and then following policy pi thereafter. So if you find yourself in state S and follow policy pi, the value that's assigned to that state S, p sub pi of S, is given by the equation you see there. It's just the expected discounted return that you expect to see for being in that state. Similarly, the action value function, or sometimes called the Q value function, is similar, but in addition to being in a particular state, it also takes into account taking a specified action under that policy. And the Q value is denoted to be Q sub pi, and now you have a pair of variables here, not just the state, but also the action. And again, you see on the bottom, the Q value for a given state action pair is the expected return you expect to see for being in that state and taking action A, and then following that policy pi thereafter. And that return is a discounted return, as you see in the summation at the end there. So now, given this concept of a policy or a particular way of acting, let's talk about optimal policies and optimal value functions. So there's always one policy that in any MDP is better than any other policy that you could follow for that MDP, and that particular policy is given the name the optimal policy, and it's denoted pi sub star. There's also an optimal state value function and an optimal action value function. The optimal state value function is b sub star of S, and that means that you will, it's the maximum policy that you could follow for being in state S, and it's the maximum return that you could get if for everything that you know currently about that environment. The optimal action value function Q of SA is the maximum of all Q values that you can return for all the maximum maximum returns you could get for following any particular policy, and it's the optimal policy is the one that follows the one that would give you the best return or the most return. So just as a summary, today we've talked about, again, reviewed the Markov decision process. It consists of an agent and the environment. The agent can take actions, and those actions are fed to the environment, and the environment responds with a reward signal and a next state that the agent has put in. That reward signal and next state are given back to the agent, and the agent uses that information to determine what it wants to do next as it navigates the environment and tries to determine optimal policies to follow that would give it the best return and solve the environment. So we discussed the concept of states, actions, rewards. We discussed discounted return. This is the overall return that you get through all time. It discounts future returns to evaluate what the current total return would be for being in the state. If it's a V return, or a state action pair if it's a Q type of value function. So those are the state value functions V and the action value functions Q that we talked about. And then we discussed policies, and in particular optimal policies, the best policy that could be followed. So with that, that ends today's webinar. Let me just check before we leave to see if there were any questions. And it doesn't appear that there's anything in the chat window. So that concludes today's webinar, and I hope to see you next week when we talk about the taxi cab problem and discuss some of the interesting aspects of that famous problem in the reinforcement learning domain. Also remind everyone that's watching live that we'll transition now to an Ask Me Anything session, and I'll be on Slack for the next 30 minutes, and you feel free to ask anything about today's webinar, or really any questions you might have on anything you're working on in the nano degree to this point. So with that, I'll say goodbye and see you next week. Bye.